Okay, so let's now start this webinar. First of all, welcome to all of you for this webinar. My name is Iqbal Singh Josan, and I'm going to present this webinar, Wireless Link Engineering Part 1 of 2. You can interact with me by texting me in the chat box at the bottom left of your screen. And this webinar is otherwise listen-only mode, but you're welcome to ask any questions, and I'll respond to that. Okay, so this is the outline of the various topics we are going to cover today in this webinar. Overall, we'll cover the different RF propagation characteristics that are very crucial for any designing any wireless link. We'll talk about frequency considerations and various types of propagation modes that the RF waves go through, and also the various losses that are encountered by RF waves, like free space loss, reflection, diffraction, K-factor scattering, and we'll also learn about what was the role of all these losses while doing link budget analysis. So we'll learn a little basics about the link design fundamentals, the role of radio signal power, and how to go about the link budget analysis, along with some practical examples too. So I hope these topics will be of practical use to all the people who are attending this webinar. But I always welcome feedback. If you think something more can be added in this webinar feature, you are welcome. You are welcome to suggest anything. Okay, so let's start now with the first slide. Now, as many of you who are already working in the RF area, you must be realizing that the radio channel is the most limiting factor in any wireless link design. Well, we can have very powerful transmitters and very powerful, very sensitive receivers, but if the radio channel is not good, we simply don't receive our signal. This you must have noticed when you have your cell phone with you and you are inside a building and the signal fades. You simply cannot receive a signal. So that's why the radio channel, the RF propagation is so important factor in designing any wireless link. Well, in general, the key parameters that impact designing a wireless link, we have frequency, of course. What frequency we are using to transmit our signal, that is of importance. What is the path of propagation? Like, is it line of sight? That means, can my handset see the cell tower eye to eye, or cannot? Or otherwise, am I inside a building and getting a reflected signal, a diffracted signal, or a scattered signal? Am I in an urban area where I'm surrounded by skyscrapers and it's hard to get a radio signal at all? Or am I inside a building or inside a tunnel? So there can be so many different environments where the radio waves have to propagate, and we must consider the various modes of propagation in these spaces. Well, then comes the propagation medium itself. Is it free space? Now, free space means that there is nothing between the transmitter and the receiver. But of course, if you are on Earth, you always have something. You have air, you have oxygen, you have water vapors, you have clouds, you have raindrops. So all these things do impact the propagation of radio waves. And then, am I in the lower atmosphere of the Earth or in the upper atmosphere? Well, as we'll see in a few slides later, that how the atmosphere itself affects the propagation of radio waves. Okay, so let's first look at the frequency considerations. Now, the International Telecommunications Union has defined radio frequency bands. So these are well defined. If you go to the ITU website, you will find this classification there. So starting with the very low frequency, 0.03 to 0.3 hertz, and going up to terahertz, all these frequencies have bands. And most of the cellular communication takes place in band 8 and band 9. Now, band 8 is very, very low. 300 megahertz is hardly used these days. But most of your UMTS, 2G, 3G, and your LTE radio communication links, they are in the UHF band, band 9. And many of your TV broadcasts are also on this band. But other frequency bands are also used for very different types of communications. Like, it may be used by military, may be used by emergency response services, and many other different types of services which are used for public service. So whenever we are designing a wireless link, the first thing is that which band of frequencies we are operating in. Now, next comes the path of propagation. Okay, I think there is a question here. What factor generated the allocation of these bands? Why these numbers only? Well, for this you have to go into the how ITU works. Well, it's a, you know, ITU is a multinational organization. All countries in the world are members of ITU. So it's more of a democratic organization. So there is a bit of history into play that how radio frequency use started. So sometimes you once a frequency band is allocated in a country, you cannot assign it again to for a different use. So all these political as well as democratic factors come into play for allocating these bands. Then there will be some technical aspects too, like some frequencies cannot be used for some particular application and some others can. So there could be some technical, it's a combination of so many different factors. If you want a detailed answer, maybe you visit the ITU website, and they must have a section there where they explain how we arrive at these frequency bands. Okay, let's move on to the path of propagation. So there could be line of sight propagation. Now, very simple example is tower to tower, a cell tower talking to another tower. This is line of sight. Or your dish antenna that you use for satellite, for receiving your TV channels, it's line of sight too. It's line of sight with the satellite. Well, in rural areas, it's another application. You don't have any tall buildings. Your handset may be in line of sight with the cell tower. Well, the story is different in urban and suburban areas where you have so many objects around you that it's impossible to avoid reflection, diffraction, scattering, and so on. Okay. Same is the case for interior, building interiors and inside the tunnels. You are bound to suffer reflections. So all these factors will become more dominant. There is no line of sight. There's hardly any line of sight. Maybe when you're inside a building, your PC or your handset is near your Wi-Fi router, and you may be in line of sight. But you go to another room, then you are not in line of sight. You are depending on your reflected or scattered signals. Well, then free space. Now this free space picture is just a metaphor. Now free space doesn't mean you have to be in outside space. Even on Earth, assuming that you have nothing in between your transmitter and receiver, you assume there is free space, and then compensate for other factors like presence of oxygen, presence of water vapors, presence of raindrops, and so on. We'll see that later in later slides how we do that. Well, then you have the lower atmosphere. Lower atmosphere is the troposphere, which is up to 6 miles above Earth's surface. So this has unique characteristics and affects the propagation of RF waves in a specific way. Then you have the ionosphere, which is 30 to 400 miles above the Earth's surface. It largely consists of ionized particles in the air, which is ionized by the radiation from the sun. And because of the ionization, it has different RF propagation characteristics. And we'll see how we make use of that in our long-range communication. Well, of course, if there is a rainfall, it's cloudy, that affects too. This you might have noticed, some of you, if you are receiving your antenna to receive your TV broadcast, you will see that when it's a thunderstorm or a cloud, then your signal does suffer actually, because the raindrops absorb a lot of energy. And when it's a clear sky, your signal might be much better. Now, before we move on, let's review what we have learned so far and have this interactive question. You can type the answer number in your text box at the bottom left of your screen. So which of the following do not impact wireless link design? Wavelength, absorption of RF waves by human body, underground and underwater RF propagation, ambient light in the propagation medium. So take a moment and just type in the right answer. Well, the right answer is 4. Very good. You know, wavelength, if we talk about frequency, then frequency and wavelength are basically the same thing, different ways of saying the same thing. So with frequency or wavelength does affect our design. Absorption of RF waves by human body, yes, it does. Human body mostly consists of water, like 70 or 80%. You can check the numbers. But yeah, the presence of liquids inside the human body does absorb RF waves, or we can even reflect RF waves. Underground and underwater RF propagation, yes, the presence of water does affect how RF waves will propagate inside water. Ambient light in the propagation medium. No, this does not. See, light is definitely it's an electromagnetic wave, but it's a very high frequency. We don't have to. It doesn't have to interfere with the frequencies that we use for our radio propagation. So number 4 is the right answer here. Okay. So now let's talk about a little about the RF propagation models. Now, since it's so complex, there's so many phenomena going on during RF propagation. How do we represent this behavior? So we do come up with some empirical mathematical models, which are functions of frequencies, path of propagation, and the medium itself. Now again, because there are so many situations and scenarios as we just briefly talked about, it's not possible to have a single model for all of them. So you have to categorize them. Like I may have a category of models for indoor propagation when I'm looking at wireless LAN, my Wi-Fi services. And we may have a separate set of models for open spaces, a different set of models for downtown areas where we have skyscrapers. So we really have to define models for different situations. And for each of these situations, there may be so many different scenarios. And a lot of experimental work is involved. Like I can't, like no professor or researcher can just write an equation that describes all of them. We really have to go out in the field and do some drive tests, collect some data to understand the behavior of RF propagation. And then put these large amounts of data, large collections of data into some empirical mathematical form. And those mathematical forms can be used for our future analysis for similar situations in the future. So that is why different models will exist for different sets of unique constraints, such as indoor or outdoor. Well, there is another question. Very good. Is it possible to have a general model and then apply specific boundary conditions to zero on the custom model? Do such models exist? Well, as I said, like there are general models, but then they will have limited application because each scenario situation may not be exactly same as the other one. You have to modify or compensate for additional effects. Or definitely there will be a general model to begin with, like free space loss is a very general model. But then you have to add more things to it to arrive at the total loss of power in RF propagation. So it's basically we have to suit the models according to the situation, suit the general models and customize them according to our situation. Okay. I hope I answered your question, but yeah, if you still need more clarification, we can always communicate with me offline, send me email. Okay. Now, what does an RF model predict? Well, the first thing we want to find out is the large scale variation. Like if I'm at a distance d from the cell tower, how much signal level will I receive? Now the transmitter may be transmitting 40 watts, but that does not mean my handset is also getting 40 watts of power at its antenna. It depends on the distance. Like the far away I am from the cell tower, the less signal will I receive. The power decays, the RF power decays. So large scale variation is what I am looking at when I am looking at any RF propagation model. So other thing I want to see is what is my small scale variation. Now what is small scale variation? That means I am at a specific location, but if I move around the area, like let's say I'm in my office, and if I go inside the building or outside the building or move around the building, my signal will change actually. You know, you can see the bars on your cell phone. The bars will go up and down. Some places, some locations within the same area, the signal will be strong, and some locations it will be very weak. So those are small scale variations. And the primary reason for those happening is because I am receiving my radio signal from multiple sources. Multiple sources means multiple paths. There is, as you see in this picture, path 1 is we have a reflected signal from a hilltop. In path 2, the signal is coming from reflected from the building. The only path 3 is the line of sight directly coming from the cell tower. This is just an example, but in some cases, your cell tower may not be visible at all. All you get is reflected copies of the signal. And all these signals, when they arrive at the handset antenna, they will add or subtract each other because they'll be reaching out of phase. Because why they are reaching out of phase? Because they are transversing different lengths of distance, different lengths of paths. And this can result in fading. This is called fading. Up to 20 or 30 dB of fading. Your signal can fall below by 20 to 30 dB just because of this small scale variation. It's not large scale variation. If there were no buildings, no hilltops, then your signal might be 30 dB stronger, provided you are in line of sight with the cell tower. But just because of fading effects, your signal is becoming weak here. So that is the other application of the RF models. Now let's look at the frequency considerations, the way ITU has divided the frequency regions around the world. So there are 3 regions. Region 1 is Europe, Africa, Middle East, and North Asia. Region 2 is Americas. Region 3 is rest of Asia and Australia. So it's a very controlled resource basically. You know, the frequency, you can't just transmit anything anywhere. You have to look at what type of frequency bands are available in your region, and then you design a link for that. So let's look at the ground wave propagation. Begin with the ground wave propagation. This is one mode of propagation that the radio waves follow. Now, in ground wave propagation, the radio waves follow Earth's curvature. They just follow the curvature. You see here, the spherical ones, they just follow the Earth's curvature and reaching the antenna on the other side. So waves do not leave troposphere. They remain within the boundary of 6 miles above Earth's surface. Surface waves, they have actual contact with the ground. There is also direct wave, direct line of sight propagation from the transmit to receive antenna. There can be reflected or diffracted waves too. There could be objects here or from the surface of Earth itself that the waves are getting reflected. Now, which frequencies follow this ground wave propagation? Less than 3 megahertz. This is very small frequency. You don't use this for cellular communications. This is used for radio navigation, maritime mobile service, and some public radio broadcasts. Your AM radio stations use this frequency. They are in the kilohertz range, right? If you remember. So they do have their uses, and they have specific uses too. So in this table, you see all these frequencies which follow ground wave propagation. Now, what are the key parameters which are affecting ground wave propagation range? First is the frequency. Higher the frequency, lower the range. Now, this is a very general fact about any frequency actually, not only ground wave but other waves too. Higher the frequency, lower the range. Ground conductivity, higher the ground conductivity, higher the range. That is why if you are transmitting less than 3 megahertz over the surface of ocean or salt water, you will have best performance. And that is one reason why maritime services use this frequency band, because they perform very well over the surface of water. The ships talking to other ships, they can use this frequency band with excellent success. Now let's go to ionosphere wave propagation. Well, okay, there is a question here, why high frequencies are low range, please? Well, when we go to later slides, we'll talk about the free space power loss. So with frequency, the power decreases actually. If you higher frequency, lower power. There is a direct mathematical relationship. This is a property of electromagnetic waves. So that is how we get that. Okay, so in the ionosphere or sky wave propagation, you know, over the surface of Earth, from 30 to 400 miles, we have the ionosphere. We have D layer, E layer, F1 layer, and F2 layer. This you can find in the literature. It's very commonly understood. Now, this ionosphere, these layers, they consist of ionized particles in the atmosphere. And once they are ionized, the refractive index of the medium will change. And once the refractive index of the medium changes, what they will cause? They will cause refraction in the ionosphere. Now, refraction, if you go back to the properties of light waves, how light waves can refract when they pass from a medium of higher refractive index to a lower medium to a lower refractive index. The same thing happens here. These RF waves too, because of the changing properties of the refractive index, which decreases as we go up in the atmosphere, these can get refracted. Now, this is not reflection, this is refraction. Just because the index changes here, this RF wave, instead of going up into space, it gets refracted, it comes back to the receiver. Now, this has very good uses. You can increase the range of your radio communication, which won't be otherwise possible. Now, but they have a downside too, because this is ionosphere, its properties of refractive index will change from time to time. It's not static. It will change with the time of day, with the location, with season, with the solar cycle, or with the solar rotation. And what that means, the propagation path is not always available. So that presents additional challenges if you have to use this band, 3 to 30 megahertz high frequency band. So ionosphere wave propagation is commonly used in this band, 3 to 30 megahertz. You have to be in this range. Again, we don't use it for cellular communication. It may be used for some backhaul links, for low rate communication, but not for our cellular communication. Okay. Now, there are a few things that we need to understand about the skywave propagation. First thing is the elevation angle. At what angle I am launching the wave into the environment? This is called the elevation angle, because this does have a bearing on how far the RF wave will be reflected and how far we can receive it on the other side of the Earth. It's also called takeoff, launch, or wave angle. Well, there are a few other terms which are commonly used when you do skywave propagation. One is the skip distance. This is the distance between the transmitting antenna and the beginning of the ionospheric return. Like let's say that it begins to return at this point, so this is the skip distance. And then there is a critical angle associated with that. Now here you see when the elevation angle is too high, there's no refraction. It's just going directly into space. Where the other RF waves which have lower elevation angles, they are getting refracted and returning to Earth at different points of Earth. Okay. Let's move to the other one. Now we can use multi-hop propagation too to extend the range. What this happens that when the RF phase returns, okay, there is a question here. Skip distance again. Okay, let me go back. So skip distance is like, you know, when let's say, okay, we begin with number 4. Number 4, the angle is very high. I'm not getting a return of the RF wave. So what I do, I start reducing my angle. So the point at which my RF wave returns, the distance between the transmit and receive is called skip distance. This is the first point of return from the ionosphere. Of course, if I reduce it further, I will have more returns at more ranges. Is that clear, the skip distance? Okay, very good. So multi-hop propagation. The RF waves which return from the ionosphere, they can be reflected by the surface of Earth and go back to the ionosphere again and be reflected again to extend range. This is a real phenomenon which happens. This helps us to extend the range to up to 2,500 miles. Now this ionosphere propagation is widely used by amateur frequency bands, the unlicensed band, where you can use this communication to talk long distances. Another phenomenon that happens with the skywave propagation is the ducting. Now ducting means that once the RF wave reaches the ionosphere, it does not return immediately. It just ducts through the ionosphere. The properties of the ionosphere are like that it just goes through the ionosphere, and at a specific point, it will refract and come back to the Earth. This is another phenomena which is a rare one, but does contribute to extending the frequency range. Extending the range of the signal when we use skywave propagation. Well, there are a few more things. When and any operator which is using skywave propagation, he has to be worry about. So one is there is a question here. Isn't that due to different permittivity of layers? Yes. In this case, okay, yeah, permittivity does have a role to play here. Ducting, yeah, about ducting you are talking about, yes. Permittivity does have a role to play here. Because of permittivity, it will stay over there and return at a appropriate point to the Earth. So critical frequency is the highest frequency that returns echoes from E and F regions at vertical incidence. So typically it will be between 1 to 15 megahertz for F region. Did I answer your question about ducting? Okay, yeah. So critical frequency is the highest frequency that returns echoes from E and F regions at vertical incidence. So now if our elevation angle is 90 degrees, what will happen? The echoes will get echoes from the ionosphere. So the highest frequency that returns echoes is the critical frequency. Of course, it's a function of electron density of a region. Higher the ionization, higher is the critical frequency. Now you might think that this is just why I'm explaining all these terms. So slowly we'll see. Okay, now this scenario we'll see. You have, so as an operator of skywave propagation, what you have to worry about? You have to worry about the maximum usable frequency. What is the maximum frequency I can use within the 3 to 30 megahertz band? Why I need to know that? Because the properties of skywave propagation are changing all the time, with time of day, with season, with solar activity, and so on. And also with elevation angle, see. In this case, you see, if the elevation angle is reduced, higher is the MUF. Now, for number 1 is critical frequency anyway, MUF is 10 megahertz. If we reduce the elevation angle to, let's say, this is 60 degrees, then your MUF is 15 megahertz. we reduce it further to, let's say, 30 degrees, your MUF is 30 megahertz. So these findings are from observation. There are agencies which publish these findings that what will be the maximum usable frequency at a certain point of time in the ionosphere. So in general, lower the incidence angle, higher is the maximum usable frequency. And by definition, it's the highest frequency supported by the ionosphere for any path between two stations. Of course, as we discussed before, it's a function of path, time of day, season, location, solar, ultraviolet, and X-ray radiation levels, and also sudden ionospheric disturbances. So it's not a very reliable path, it seems, but still it is used just for its benefits of having a longer range. Now there is also a lowest usable frequency, or LUF. So in this case, this is the lowest frequency which is supported between two stations. And also the absorption will increase at lower frequencies, but because they have lower energy itself. So here this illustration again shows how the LUF for the critical vertical incidence 90 degrees is 5 megahertz. When you reduce the angle, it's 7 megahertz. Reduce it further, it's 10 megahertz. So you get higher LUF. So there are two boundaries here. One is the lowest usable frequency, and one is the maximum usable frequency. Now LUF can be further lowered by using high power and directive antennas, or by using receivers which are less demanding of signal to noise ratio. But again, an operator needs to know about the operating frequency. Now operating frequency in this case has to be somewhere in between the LUF and the MUF. So this comes through experience. Someone who has been operating in this band 3 to 30 megahertz for a long time, he will know, like, okay, for me, for my location between two stations, this is my optimum frequency I can use between the LUF and MUF. However, there are some general models also which are used, ISPAC, VOCAP, and ITU also has some recommendations. If you go to ITU website, they will recommend some mathematical models which can be used to predict your operating frequency. Other way is that you just find out experimentally, have ionospheric sounders, which is real-time information on available frequencies. In that case, what happens? The operator will have a sounder transmitter installed here and receiver here, and just emit pulses periodically, and see which frequencies are working best at this time before actual communication will take place. So ionospheric sounders can also be used to get real-time information on available frequencies. And what that means that my frequency, my usable frequency, could change from time to time actually. It depends on what type of frequency is available right now, which can use skywave propagation, which I can use for my backhaul wireless links. Okay. Now I think we covered a lot here. Let's pause for a while and just see what we learned so far. So which of the following are false? 1 megahertz is ideal for skywave propagation. Operating frequency must be between LUF and MUF. Received signal is a vector sum of surface wave, direct wave, and reflected wave. Operating frequency is not a function of elevation angle. So yeah, very good. Number 4 is the correct answer. So even if we forget everything about skywave propagation, we have to remember that we do have to make a decision about the operating frequency. That is what of practical use to us is as an operator. I must know what is my operating frequency. I am at a certain location, my transmitter is at this location, receiver is at a different location, and I want to know what is my LUF, what is my MUF, what are my boundaries, and what is my operating frequency in between these two boundaries at a specific time of day, time of year, or time of solar cycle, and so on. And for that, I have to depend on various sources. Well, one of you has given another correct answer, 1 megahertz. Very good. Because if you remember, the ionosphere propagation is between 3 and 30 megahertz. So 1 megahertz is not ideal for ionosphere wave propagation. Okay, did I miss any question? I think we can move on. Okay, so next we have the, for cellular communications, we have the most important, the direct wave propagation. This is used very commonly for satellite links, and for all the microwave tower to microwave tower links, or from cell tower to handset links. Again, reflections are still possible. We cannot avoid reflections. Reflections can happen from ground, from nearby objects, from tall buildings, skyscrapers, and so on. Okay, so we always go above 30 megahertz bands. All direct wave propagation happens more than 30 megahertz. And the range is limited by the frequency. Again, higher the frequency, lower the range, because the power decays. Higher the frequency, more power decays. It's very commonly used for radio, TV, and satellite broadcasts, used for GPS navigation, mobile and satellite phone services. So direct propagation has many uses: wireless LANs, microwave links, GSM, CDMA, WiMAX, LTE, 4G wireless broadband, and so on. So most of the commercial uses are greater than 30 megahertz frequency bands, and it usually is direct wave propagation. But yeah, of course, additionally you will have reflections, refraction, and many other things going on. Now, another phenomenon that is important here, even for direct wave propagation, we have troposphere wave propagation. This is diffraction which happens due to changes in temperature, humidity, and pressure in troposphere. Humidity because clouds, thunderstorms, they exist in this in the troposphere. Now, this has a beneficial use for us. It extends range beyond line of sight. Now, your real horizon is extended by 1.15 times away from the visual horizon. And you can use this formula given here to actually calculate it. Like as you see in the illustration, T1 and R1, this is the actual line of sight distance. But then because of this troposphere refraction that is happening at number 3, our range is extended. This is the extended range. And extends the range to R2. Now, troposphere wave propagation, you also experience scattering. Scattering caused by rain, snow, fog, and dust. Now, here there are some relationships here. Higher the scattering volume, more is the signal strength. Why? Because if more is the volume, more RF waves will be scattered, and some of it will reach the surface of Earth. And lower the scattering angle. This is scattering angle, the theta. This is the scattering angle. Lower the scattering angle, lower the overall signal attenuation. Now, of course, you may ask me how we arrive at this. Now, these are results arrived from measurements from some modeling of this scattering phenomena in the troposphere. Researchers have spent hours of time just to model it, and people have done measurements. So I'm just giving you the results, which can be used for our practical purposes. Here, the maximum range is usually limited to 500 miles because of scattering in troposphere. Well, this is very useful for long-range wireless backhaul links, from microwave links. It's very commonly used for microwave links. And we are benefited by the extension of the radio horizon by 1.15 times. That means 50% more distance is achieved just because of troposphere scattering and refraction. Okay, let's pause for a while again. Okay, there's a question. What does B stand for? Let me go back to the slide. Which slide you are talking about, this B? The table. I'll get back to you later on that. At this point, I don't think I can answer that. Please bear with me. Let's move on. Okay, I apologize for this pause. Okay, let's back to the question first. Which of the following statements are true? LTE uses ionosphere wave propagation. Troposphere propagation uses scattering to extend range. Higher antenna height extends range, and higher frequency extends range. So which one Which one is true? Well, number one is not true because LTE 4G wireless does not use skywave propagation. Troposphere propagation extends range. Yeah, that is true. We just talked about that. Higher antenna height extends range. Yes, that is true. Higher frequency extends range. No, that is not true. Higher frequency does not extend range because higher frequency means more power decays. You get less power at the same range. Okay, now let's talk a little more detail about various losses that the RF waves will experience while propagating. So free space loss. So in order to model the free space loss, we assume that we have transmit and receive antenna in line of sight. Now we are arriving at a general model first, actually, right? Before we can apply the same model to different situations. So we have a line of sight and we have isotropic antennas. If you recall the concept of isotropic antennas, that the antenna is like a point antenna and it radiates equally in all directions in a sphere, actually. That is an isotropic antenna. Now, if we consider that, we know that the received power decays as square of distance. The farther you are from the transmitter, the less power you get as square of distance. This is because the RF energy disperses in all directions from the source. With this mathematical formulation, you get 6 dB per octave of reduction. That means when the range is doubled, the power is lowered by 6 dB. And received power also decays as square of frequency. That is why higher frequencies will have more decay. 6 dB per octave or 20 dB per decade again. And also there's another factor, like at higher frequencies the antenna dimensions are smaller because the wavelength is very small. That also allows less RF energy absorption. You could achieve deploy other means to increase the RF absorption, but this is a fact. The antenna is smaller, so it can receive less energy too. No, it is not caused by space. This is the characteristic of electromagnetic waves. This is not caused by the receiver or by the space. This is a property of radio waves itself. Higher the frequency, as it travels longer, it loses more energy. Now this is a physics question actually. We have to go back to the physics of it to understand. But this is the result we get. This is a very, very standard result we get out of that. RF is radio frequencies. Yes, the material medium remains the same. Free space means, that is why we are assuming free space here. Free space means we exclude all other effects actually. It's just the transmitter and receiver, nothing in between. This is an ideal mathematical model. So if you go into the physics of it, you arrive at this formula. You don't have to remember it, but just look at the what it reveals. The received power in the Fry's equation for far field received signal. The received power is a function of the transmit power, the gain of the transmit antenna GT, the gain of the receive antenna, the wavelength, and the distance. Okay. Where we have this term called EIRP, equivalent isotropic radiated power, which is the product of the transmit power and the gain. Well, this is a more at the bottom of this slide. You see the free space power loss. This is a very practical formula which we are going to use in our link budget calculations, because this is the form of dB. It gives you the free space loss in decibels. In dB, you just input the values of frequency in megahertz and the distance in kilometers. Just do the calculation and you get the free space power loss. It tells you how much power you will lose for a certain frequency and for a certain distance. Okay. Now let's go to a little example of a microwave link. Microwave link, this is the formula we are going to use, the free space loss formula. Now case 1, we have frequency 1 gigahertz and distance is 30 kilometers. We arrive at a free space loss of 122. Case 2, now here we keep the frequency same, but we double the distance. From 30 kilometers we go to 60 kilometers. We get more free space loss, 128. Yes, this is log base 10. It is log base 10. Okay. So you see there's a 6 dB more power loss here. From 122, we have more loss at 128 because we double the distance. In case 3, now what we do, we double the frequency to 2 gigahertz, but we keep the distance same, 30 kilometers. Again, you have 6 dB loss. From 122, just by doubling the frequency, you come down, you have more, you add another 6 dB of loss, 128. Okay. I hope this explains the practical application of this free space loss. Well, 32.45, this is because when we convert the Fry's equation to dB form, we get this quantity there. You just have to add it. This you can do. You can do a log. You can do a mathematical calculation. You can do a log of both sides of Fry's equation, and with base 10, and you will arrive at this quantity which you have to add. So it's just mathematics, nothing else. No physical significance. It's the same equation represented in dB form. Okay. Well, let's go to the next phenomena, reflection. Again, in order to model the reflection, the phenomena of reflection, we assume that this is a line of sight path. There, from transmit to receive antenna, there is a line of sight path, and there is a reflected path too. We are assuming that the reflection is happening from the ground here. Of course, we have the height of antenna HT and height of receive antenna HR. Now, in this case, the received power decays as fourth power of distance. There is more loss here because we have a reflected signal also, which is cancelling out the line of sight signal. So it is 12 dB per octave. What that means that if you double the distance, there is a 12 dB loss in additional loss in power. Received power increases with antenna height. So this is in our favor. How do we overcome this loss? We increase the height of antenna. If you increase the height of, if you double the height of antenna, you get a gain of 6 dB power level. And also received power increases with antenna gain, of course. You get more gain on the antenna side, on the transmit antenna, or more gain on the receive antenna. You get more power. So again, this is the equation, but let's go to the fourth power of distance. Well, if we have these assumptions, we have like nothing in between. This is a very simple model. In this case, the fourth power distance will not change. But of course, you are right in one way, but when we go to very complex scenarios where we have multiple reflections happening, right? Multiple, as I told earlier, one scenario where inside the downtown with skyscrapers, we have multiple reflections. There, this fourth power might change actually. It may not be same. It may be fifth power, sixth power, something like that. But in this simple scenario, it is fourth power. You have to increase both antenna heights. But of course, even by increasing one antenna height, you will get very good results. See, usually it is possible, it's very easy to increase antenna height of the transmitter at the time of installation. But like if you have a handset in your pocket, you cannot increase your own height actually. Whatever height you have, right? You could rise to the rooftop to get a call, but that is not a very practical scenario. So really we are talking about increasing the antenna height of the transmitter here, the cell tower. And it makes more sense that way. But of course, it's a fact, like if you go up in the building, your signal will be stronger. If you go up to the rooftop, your signal will be stronger. Okay. Now this is a very practical equation we arrive at to calculate the effects of reflection in this simple scenario. Again, you just enter the gain of the transmitter, receiver, the height of the transmit antenna, the height of the receive antenna, and the distance. Okay. Now let's take one example again to understand this a little better. We arrive at this simplified model. Again, I'm telling you, this is a simplified model, right? If situation changes, the model will change definitely, and that's why we can't have a general model for everything. Now, just to understand the behavior of this, let's take case one. So here, you have the gain of the antenna. We have 24, the transmit antenna. Gain of the receive antenna is 20. Height is 40 meters for the transmit, and height is 1 meter for the receive antenna, and the distance is 10 kilometers. We come to a loss of 84 dB. Next, what we do, we keep the gain same for transmit and receive. Height remains the same, but the distance doubles. If the distance doubles, we have additional loss here. How much is it? 12 dB, right? Okay. Case 3, we double the gain of transmit antenna. Receive antenna is the same gain. Height remains the same for both transmit as well as receive. And the distance also remains the same, the 10 kilometers. Here we have 60 dB. You see, the power loss reduced from 84 to 60 here because we added 24 dB of gain on the transmit side. So just add 24. I mean subtract 24 from here so that we have less loss over here. In case 4, your gain remains the same, but your height increases. We double the height of transmit antenna from 40 meters to 80 meters. Now you have power loss is 78 dB. It's reduced by 6 dB. So there is a question here. So as transmitter gain increases, power loss decreases, right? Yes, that is right. If we increase the transmitter gain, power will be less power because we have more power transmitting from the antenna itself. That is right. Okay. Now there is another interesting phenomenon called diffraction, which happens with light waves also. RF waves can pass behind solid objects with sharp edges such as mountains or hilltops. Okay, there's another question. How are the constants 10, 20 and 40 coming? Again, this is a mathematical constant which is coming in when you simplify the formula to make it in a decibel form. You just do the calculation, take the Fry's formula or whatever formula is there, the basic physics formula, apply log on both sides, make it in decibel form, and then you get these quantities. So it's just, there is no physical significance of it. It's just a mathematical formulation. Okay. So radio waves can pass behind solid objects. Now here you see there is a barrier looking like a hilltop or a mountain standing between the transmit and receive. And there is a shadow zone here behind the hill. The signal just cannot go through. There is no line of sight signal. But due to diffraction, the radio waves can reach the top of the hilltop and bend around the hilltop and reach the receiver antenna. Still you will receive signal. Well, somebody said this is the classic case of knife edge diffraction. Very true. That is very correct. Go to any textbook, it will describe that. It happens for light waves as well as radio waves. Again, this phenomena is of very good use to us. Even if we have objects blocking our line of sight path, we still can receive signal on the other side in the shadow zone. Now let us see the behavior of this a little more. Now here, but we decrease the height of the barrier. Now it's a fact, like if we have the clearance between the line of sight path between the transmit and receive antenna and the knife edge, this is called knife edge, somebody said it correctly, it's knife edge or the hilltop or the mountain top. If the clearance is more than one wavelength of the frequency that we are using, then there are no additional losses. The line of sight path has no impact. We just keep business as usual actually, as if this object was not there at all. But the situation changes when we have the clearance less than one wavelength. That is when we have additional losses here. It will start interfering with the line of sight propagation. Now here you see the mathematical formulation of this phenomena when you have a height h above the line of sight and there is a Fresnel-Kirchhoff diffraction parameter. This is a lot of physics here. We're not very practical formula, so you really have to go to numerical techniques to compute a diffraction gain. That how much signal gain we have because of diffraction in this scenario. There are ways, numerical methods available to calculate that, but it's not very simple and straightforward that you can use a paper and pen to do that, because you compute this diffraction integrals here. If you can't do that, the other method is do experimentation, do practical measurements. Drive to the site and see how much signal power you are actually receiving. That can always be done. Well, then comes the refraction, in particular the tropospheric refraction. So how much the radio waves curve through the ionosphere, it depends on the change in refractive index. So this is the mathematical formulation of this wave radius and the refractive index and the height. Again, the same thing, you can read this at leisure, but any textbook will describe that too. I just put it there just for reference. Curvature is inverse of radius, of course. So how do we compute the range in this case? You know, here it's not just the wave curvature which is coming into play here, but also the curvature of the earth. Earth has curvature too. So our range will depend on the difference of these two curvatures. curvature of the wave minus the curvature of the earth. And to do that, there is a factor defined called K factor. K factor is the ratio of effective earth radius and real earth radius. So to do our calculations, we calculate a K factor, which is the ratio of effective earth radius and real earth radius. And it is defined as you see in the box here. Now, there are some interesting observations here. If the K factor, the value is more than 1, what that means? We have longer range. What that also means, the effective earth radius is bigger than the real earth radius. And if K factor is less than 1, but of course a positive value, the range is short. So effective earth radius in that case is smaller than real earth radius. So this is how we try to characterize this tropospheric refraction. It's just a K factor. When we come to practical application, it's just a K factor. We want to know what is the K factor for our specific scenario. Is it less than 1 or is it more than 1? And that will give us an estimate of the range we are going to have because of the troposphere refraction. Okay, so now here you see in this formula shown here, we are actually using the K factor, the value of K factor to compute the distance, the transmitter line of sight distance. As we said before, that our range gets extended due to troposphere refraction. And this is the formula we can use, where R0 is the Earth's real radius, HT is the height of the transmitting antenna, and K is the K factor. So K factor A is crucial to compute our distance, the range that we are covering with our transmitter. And total line of sight distance, HT is the height of the transmitting antenna. Somebody asked this question, what is HT? So HT is the height of the transmitting antenna. Now here, the total line of sight distance, we take both distance covered by the transmitting antenna and the distance due to the receiving antenna. How far the receiving antenna can see beyond the horizon. So we do it twice actually. We add the DT and DR and take the heights of both transmitting antennas and the receiving antennas. HT is the height of transmitting antenna and HR is the height of the receiving antenna. That helps us compute the total line of distance. Well, let's take a microwave link example because the troposphere refraction has more uses over there for the tower-to-tower communication. So here we take the value of the Earth's real radius R0, and HT is 30 meters, the height of the transmitting microwave tower, and HR is the receiving one, the other side, 25 meters. And K, we take it 1.33. This is for standard atmospheric conditions. This is a very standard value. If you don't really know the value of K, you can use this value, 1.33, assuming this is the value for standard atmospheric conditions. When you have clear sunny sky, there are no thunderstorms, and the ionosphere is stable, and so on. Of course, this might change, but then it might change from this. Like it may become less than 1.33, maybe 1.2 or 1.1. There may be some variation, but for all practical purposes, you can use the value of K as 1.33. Of course, online you will find resources which ITU site is the best resource. Go to the ARRL, American Radio Relay League site. They also publish the values for K factor. And using that, you can now compute or you can estimate the line of sight distance between the two towers. It's coming out to be 43 kilometers in this case, in standard atmospheric conditions and with the given heights of the transmitting and the receiving antenna. Okay, let's pause for a while. Let's see where we are. Received signal power increases with what? Distance, frequency, receive antenna height, receive antenna gain, transmit antenna height, transmit antenna gain, diffraction, reflection, or scattering. Well, okay, very good. You are coming up with some responses and thinking about this. Very good. So the correct answers are 3, 4, 5, and 6. 3, 4, 5, and 6. Of course, we have seen with distance, the power does not increase. It rather decreases. Power decays with distance. With frequency, no, it does not increase. It decays, actually, right? Receive antenna height, of course, that plays a part here. More the height of the transmitter and more the height of receiver, yeah, more will be the received signal power. Transmit antenna gain and receive antenna gain also play a part here. Of course, the diffraction, reflection, scattering, they always dissipate power. Very good. Let's move on to the next slide, next portion of this. Now, scattering. Objects smaller than a wavelength will scatter radio waves. Very practical examples: street signs, utility poles, foliage. Foliage means trees, forest. Irregular landscape, if you have undulating landscape, like somewhere you have a ditch and somewhere you have a hilltop, all these will scatter radio waves. Now, there is a criterion used to define the roughness of a surface, electrical roughness of a surface. It's called Rayleigh criterion. And that can be used to define a surface. As you see here, this is a simplified model of scattering here. You see, ray number 1 is reflected from an object of height h. So it is scattered because there is an object at h here. Ray number 2 is reflected from the smooth surface here, number 2. Of course, both are incident in the same angle of theta, but because of this object of height h, there will be a phase difference between number 1 and number 2. And because of this phase difference, they will try to cancel out each other, and the RF energy will be scattered. So in general, if there is no path difference between the two rays, is path difference 0, then it's a reflection. But if the path difference is, let's say, half wavelength or even different than 0, then the surface is scattering. You know, there is a very fine transition from reflection to scattering. Reflection is when we have very ideal scenario, everything reflected at the same, reflected from a smooth electrical surface, no path differences involved. Then, of course, yeah, it's just a reflection. But the ideal conditions are not like that. We never have a very smooth surface. We always have some objects here. We have, in the real life, we have objects which would reflect the same radio waves in different directions, and that will cause scattering. So the Rayleigh criterion defines this criteria, that if the path difference is less than quarter wavelength, lambda by 4, then we can say that the surface is electrically smooth. Well, for practical uses, we have this criterion. What that means, I'm sorry, what that means that it will have no or minimum impact on our received signal power if the path difference is less than quarter wavelength. But if it is more than quarter wavelength, then the surface is rough. That means we'll have more loss of signal power. So in a real scenario, like we are setting up a cell site, and it's very important what type of landscape we have over there. Is it a very smooth surface, no hills? No, it's very flat. Like in Texas, it's very flat. But if you go to Boston, well, it's very hilly. You go to Seattle, it's very hilly. So we have very different landscape. So based on this criterion, you can determine whether a surface is smooth or rough. Well, where is this criterion used? Of course, it is used when we are designing electromagnetic measuring sites, or when we are trying to calibrate antennas. You know, go to any company that manufactures antennas, these cell towers. They always have a calibration range, and they will use this Rayleigh criterion over there. They will actually simulate those rough and smooth surfaces to see how their antenna performs, how the signal level changes. Well, somebody commented that depends largely on frequency of operation. Well, that is true. If you see in this formula, we have this lambda. Lambda is wavelength, and of course, frequency also determines the criterion. Like what height of object h is tolerable actually. So for a smooth surface, how much, what height of object h or irregularity here you see in the picture of height h can be tolerated. If it is more than h, that value of h, of course, then the surface is tough. Is that lambda the center frequency of operation? Yes, that is true. So V is the center frequency of operation. Let's say if you have frequency 900 megahertz, you can calculate the wavelength from there. It's a very straight formula. So that is the wavelength corresponding to that center frequency of operation. Of course, if you have a frequency band like 25 megahertz band, then of course the band has to be considered. But here we are concerned about the center frequency. Now there is a relationship with the grazing angle theta. The grazing angle is the angle at which the RF wave is incident on the surface. Here in the table, if you see, there are some interesting observations here. At a specific frequency, like say 900 megahertz, if you increase the grazing angle, the H reduces to just like, for 60 degrees, it's only 5 centimeters. That means if I am transmitting or propagating at 900 megahertz and my angle of incidence is 60 degrees, 5 centimeters of objects will not do me any harm actually, right? So it's very, very small here. My tolerance level is very small. But here, if grazing angle is high, my H has to be less than 2.36 meters. Now if I double the frequency here, okay, there's a question, grazing angle definition again, please. Okay, let me go back to the previous slide. This is the grazing angle. You see, the ray 1 is incident on the object at angle theta. This is the grazing angle. Like for a practical example, like if you have a handset and there is a cell tower. If you are very close to the cell tower, your grazing angle is very high. It may be 70 degrees or 80 degrees, like, right? If you are far away from the cell tower, your grazing angle is small. It may be only 10 degrees or 20 degrees or like that. Does that make it clear? Okay. So you know there is a relationship with the grazing angle and the frequency here, and you can see the trend here. If you double the frequency from 900 megahertz to 1800 megahertz, you know your tolerance is only 1.18 meter here. So you need a height of only 1.18 meter to make it smooth. Any object higher than 1.18 meters will make it rough. But if you increase the grazing angle, like that means if you move closer to the cell tower and you have a frequency of 1800 megahertz, any object greater than 2 centimeters will make it rough, and you will have more loss of signal power. Well, yeah, of course, this is a visual picture in the table, but it explains the facts, how the grazing angle and the frequency determine your scattering, how much scattering you are having actually. And that is a function of how far you are from the cell tower. Okay. Now this is pretty straightforward. The presence of oxygen and water vapors, means clouds, rain and fog, also cause losses. They also absorb radio power. For that, it's pretty much standardized. You don't have to do much because these numbers are published by ITU and ARRL and other organizations. And here you are talking about how many dBs per kilometer of losses are there for oxygen and how many decibels per kilometer of losses are there for water vapor. And you just add them up and find out what is the total atmospheric loss for RF wave. There is a table here. This is available on ITU website too, and many variations of that, which can be used to determine the specific attenuation, dBs or decibels per kilometer versus frequency. So here you see, you just see where your frequency is and see in the graph and how much specific attenuation you want to use for your calculations. So this graph can be used for your calculations to determine atmospheric losses. Well, okay. Let's talk about now link budget analysis. Many of you must have already heard this or maybe doing it even. Like I see some of the people. Wait a minute, there's a question here. One topic we discussed way back, what is the difference between tropospheric and direct wave propagation, as they both work for greater than 30 megahertz? Or let's keep this at end. Well, that is fine. Well, direct wave propagation is like line of sight. But direct waves within the troposphere, they get refracted too. So they work together actually, you know. Tropospheric wave propagation actually helps us by extending our range of direct line of sight propagation. If you go back to some slides, yes, greater than 30 megahertz. This is greater than megahertz, 30 megahertz we are talking about. Yeah. More than 30 megahertz we do have line of sight, but we do get help from troposphere refraction too by extending our range when we are transmitting more than 30 megahertz. Even in VHF or UHF, our range or radio horizon gets extended. and we had a formula to calculate that, how much of our range is extended. They both work together actually. If you still need more clarification, we can do it offline. Okay. Okay, so what is link budget analysis? So here we actually see ultimately what I want to know here. I just want to know what is my received signal to noise power ratio for a wireless link. I need to have enough signal power on my handset so that I can receive my call, so that I have enough bars on my cell phone, showing on my cell phone, to make it usable, right? So our whole object here in link budget analysis is to calculate the ratio of received signal power to noise power for any wireless link. And we do this from, we need to know what is the transmit power, what is the antenna gain on both sides, transmit as well as receive, what are all the losses in between transmit and receive antenna, and what is the receiver noise level. You know, any receiver will pick up not only signal but also noise that is present all around us. And what is the required fade margin? Now, where this fade margin comes in, as we discussed before, your signal can fade from location to location. You are inside a building or outside a building or in a different location or behind a hill, your signal will change. So that means I need to keep some allowance to overcome the fading effects. So what are my fading effects? How much dB do I need for my fade margin? So all these factors come into play when I do my link budget analysis. Now let's first look at the generic wireless link. That is how I'll go about the link budget analysis. So we have at one end on the top left we have the transmit parameters. So what are the 3 parameters here? We have transmit power, the losses inside the transmitter, like we have a transmitter equipment, and there will be some cables connecting from the equipment to the transmit antenna or the cell tower, and we have losses there on the transmission line too. Then we have the transmitter antenna gain, GT. Next we have a set of parameters called link parameters. Now these are the radio channel parameters, the things we have been talking about. Yes, gain is a kind of ratio. Gain is a kind of ratio, yes. So link parameters. We have free space loss, we have atmospheric loss, and we have additional losses. Additional losses will depend on what type of things are happening. Is reflection happening there? Is scattering happening there? Is diffraction happening there? And so on. So on the receiver side, we have the receive parameters, where we have now noise comes in here, because the receiver also picks up noise from the environment. So we have several sources of noise here. We have the natural noise, NNet. We have the antenna noise, comes from the antenna. We have the feeder loss noise, NFL. We have the receiver noise, the noise generated inside the receiver equipment. And then we have receiver gain, GR, receiver losses, and received signal power, PR, is the final power we get. Now this is our object. We want the result to be a ratio of received signal power to noise ratio. So these are all the blocks that we need to compute when we are doing a link budget analysis to arrive at a received power to noise ratio. How do I do that? Okay, let's go through it. NFL. Well, NFL is the feeder loss noise. The feeder from the receive antenna to the receiver equipment. There will be a loss of power over there because of transmission losses, and it will generate noise too. It will contribute more noise. Now this is not generally for handsets. The feeder is not very long. Handset antenna is inside the handset, so NFL will usually be 0 in this case. There will be no NFL. But if you have a microwave tower, there you have a long feeder line running from the antenna to the receiver equipment, and that contributes to noise. It's noise coming from inside the transmission line. Okay. So let's simplify a little. The transmit parameters, we can combine them together. In fact, there is a very standard industry name for that, EIRP. It's called equivalent isotropic radiated power. So this is a combination of the transmit power minus the transmit losses plus the gain of the transmit antenna. So often you will, when you go to transmitter specifications, you will have this figure mentioned there, this term mentioned there. So you will ask about what is the EIRP of this transmitter. It often will be mentioned in terms of dBW or dBm. Okay. Yeah. What does it signify technically? So somebody asked that what does EIRP signify technically? So technically we are taking into account the receiver gain. We are taking into account the transmitter gain and the transmitter losses. You know, if you see in the picture here, in the slide here, the transmitted power is PT. Like we say, I have a transmitter which transmits 40 watts of power. But that ultimately means nothing unless we exclude transmission losses. We subtract the transmission losses because what cable I am using to transmit from my equipment to the antenna. I have to subtract my transmission losses, but I have to add the gain of the antenna too. What type of antenna I am using? Am I using a directional antenna, a dish antenna, or simply omnidirectional antenna? So my equivalent isotropic radiated power will be a combination of these three factors. It will combine the transmitter power, subtract the transmission losses, and add the gain of the antenna. That means effectively, what do I get out of all this? I have an antenna, I have a transmission line, and I have equipment too. So technically, that is what it means, and that is of significance to us when we are calculating signal power level at the handset. All of these factors will determine effectively what signal reaches the handset. Okay, let's move on to the next one. I'm sorry. Okay. Next, we have the link parameters. We have the free space loss, atmospheric losses, and addition losses, which could happen due to reflection, diffraction, and scattering. So the path loss will be an addition of all this. We just add up what is the free space loss, which is happening due to the distance and the frequency, and what is the atmospheric loss, which is due to the presence of oxygen, water vapor, fog, and all that. And what are the additional losses? Now, these additional losses will depend on what type of cell site you are considering. Are you considering an indoor scenario or an outdoor scenario, and how much of reflection, scattering, or diffraction is happening there? That will contribute to additional losses. So what do we have so far? We are now here combining the two, the transmit and the link parameters. So you see, effectively, we from the transmitter we had EIRP, equivalent isotropic radiated power, which is coming out into space and reaching the receiver. But then we subtract the path loss. We calculate the path loss and subtract, and this is the resulting power available to us after RF waves have propagated through this distance. EIRP minus PL is the power available here at this point in space. But there are more things to consider now after this. Somebody asked that, is it like we are excluding losses entirely from the budget analysis? No, we are not excluding. Losses are a very important integral part of budget analysis. As we see, we'll put this all together and see how this impacts it. Okay? Wait for a few more slides. So receive parameters, we have the antenna gain, receive antenna gain, GR. We have the transmission losses, LR. We have the received power, PR. And we have the noise power, natural noise, antenna noise, feeder loss noise, and receiver noise. So what do we have so far? This is how the final equation will look like. Received power will be equivalent isotropic radiated power, EIRP, minus the path loss. That means the radio waves, whatever path loss they suffered while propagating through space and reaching the receiver antenna. Then we add the receiver gain plus GR and subtract the receiver loss. That gives us the received power level, PR here. So this is pretty straightforward here. So this is the received power level here. We have the EIRP, subtract the path loss, add the gain of the receiver, and subtract the loss in the receiver. Okay. Let's pause for a while and try to answer this question. Path loss helps us determine what? Small scale variation in the received signal, large scale variation in the received signal, power loss due to atmospheric absorption, free space loss, loss due to fading effects. Okay, I'll give you a moment. Well, let's go through this one by one. So small scale variation in the received signal. So path loss does not tell us about the small scale variation, right? Path loss is like is a large scale variation. How far I am from the cell tower. That is the large scale variation. So number 2, it helps us determine number 2, large scale variation in the received signal. Then power loss due to atmospheric absorption, free space loss, loss due to fading effects. Well, again, fading effects are small scale variation. This is not true. Okay, let's move on to the next one. Now let's talk about, okay, there is a general question from somebody, Veda Prabhu. Okay, an unrelated general question. When the signal level is not high as indicated by the signal level bars of the device, does that mean I get limited data bandwidth or slower data connection? In other words, has signal strength got anything to do with usable data bandwidth? Well, here basically, as we'll see later also, there is a specification on the receiver side called sensitivity. It's a specific dB, like how much of signal level is good for the device for getting full bandwidth. It's always defined in the receiver specifications. If your signal level is above that sensitivity level, then definitely you are getting full bandwidth. If it falls below that threshold, then the bandwidth is not guaranteed. Then you have a slower connection. So from just by looking at bars, you cannot say that. The bars are only a visual indication actually, right? You have to actually look at in terms of decibels, what is the signal level? And whether it is below the sensitivity threshold of the receiver or above. If it is above, then you are getting full bandwidth. If it is below, the bandwidth suffers. So that is a very straightforward interpretation here. Okay, so now let's look at what all different types of noise power sources are there at the receiver. So we have natural sources. Natural sources come from atmosphere, from Earth, from sun, from galaxies, from cosmic background. So this is this comes from the physics of our universe. Anything that is above 0 degree K at a temperature of 0 degree Kelvin, it radiates noise. It radiates radio energy actually, which manifests as RF noise actually, and we do see it in our receivers actually. You know, if you hook up a equipment, oscilloscope, it will display like this. It will display like additive white Gaussian noise, AWGN, and it's spread out equally over all frequency bands actually, right? Now these are natural sources of noise which can be picked up by any receiver, whether it's a handset or your microwave receiver or your dish satellite network receiver. All receivers will pick up natural noise, and we have to be aware of that. Then there could be man-made sources, EMI, electromagnetic interference. You could have a nearby transformer, nearby a very high power motor running that could be transmitting some EMI pulses, and your receiver is become those too. That contributes to the noise too. Then you have antenna noise. Antenna itself will pick up the noise, which is natural noise actually. You know, it depends on where you are pointing your antenna, your receiver antenna. If it is pointing towards Earth, it will pick up more noise because Earth is at a higher temperature. If your antenna is pointed towards space, which is at a relatively lower temperature, like cosmic background is only 2 degree Kelvin, your noise will be much less. But still it will be a significant level to drown your signal, to drown out your usable signal. Then you have noise from the feeder loss, from the feeder line. The feeder line itself will have some temperature, at some temperature depending on the material which is being used there in the feeder line, that will contribute some noise. Noise generated inside the receiver. This is the bigger portion of it. You know, any receiver will generate heat because of various active devices inside the receiver. That heat will cause the temperature to rise inside the receiver. Your cell phone also gets hot whenever you are receiving a signal. So that also contributes to noise. That generates noise too, which is generated inside the receiver. So you know, noise is a big part on the receiver side. Well, yeah, a transmitter is transmitting, right? So here we are not talking about receiving. When we have a transmitter, it's transmitting. Yeah, the same antenna could also receive, and then of course, yeah, it will. Then of course it can contribute to noise. But when it's a transmitter, okay, I didn't quite understand the question. Doesn't transmitter receive its own heat or noise? Well, of course, it will receive its own heat or noise. So any receiver equipment on the transmitter side will receive that noise, right? So, you know, I'm trying to simplify things here. Like we have a transmitter on one end and receiver. It's not actually like that. We have transceivers on both ends. We have both transmitter and a receiver on both sides. So if you have a transmitting antenna and a receiving antenna side by side, yeah, of course, the transmitter antenna will also contribute to the noise, which will be picked up by the receiver on the same side, right? So that means when we are not talking about just the receiver equipment, but the transceiver equipment, which includes all the transmitting devices and the receiving devices. All of them together will generate noise. That has to be accounted for. Okay, thanks for the clarification. Okay, all right. So again, this comes from the physics. We have something called a Boltzmann's constant, K. It's a very standard value. It's a fundamental constant of the universe. And we multiplied that with the equivalent receiver noise temperature in degree K and the bandwidth. More the bandwidth, more is the noise. So KTB, just remember, it's very easy to remember, KTB. This is the basic formula we use to calculate noise power at the receiver. Noise power per hertz, of course, you eliminate B and you have KTE. Well, this is the more usable formula which we can use because we always like to make calculations using decibels because it's easy to do calculations for link budget. So this is the formula, this is the form of the same equation that we'll use. It's in the logarithmic form, but the same quantities are there. We have the Boltzmann's constant, we have the equivalent noise temperature, and we have the bandwidth. So a very little short example is given at the bottom. For equivalent temperature of 290 K and a bandwidth of 1 megahertz, you arrive at a noise level of minus 144 dBW. Now remember, if those of you who are used to working in decibels, what is the meaning of minus here? Minus means it's less than 1. It's less than 1 watt. dBW means the reference is watt, actually 1 watt. So the value is less than 1 watt here. That's the meaning of minus here. There is no negative power itself. It's just a mathematical representation in decibel form. Minus always means less than 1. So, okay. Now this is an illustration that shows some estimates of the noise temperatures on the receiver side. As you see on the natural noise, for the sky we usually take 30 degree K. This is the usual temperature of the sky. And for Earth it's 290 K. For antenna, this is a very general figure, 290 K. It can change from antenna to antenna, of course. Like if you do deep space communications, like NASA when it communicates with a receiver on Mars, let us say, or any other space organization, they may have very specialized antennas which are at a very low temperature. It may be much less than 290 K because they have to supercool those antennas to reduce the noise temperature because signal is so weak. So noise temperature for the antenna can change from antenna to antenna, but for all our Earth-based practical purposes, this is a very general number we can use, 290 K. Feeder loss is generally around 75 K, and receiver noise can range from 10 to 1000. Why such a wide range? Because there are so many different types of receivers. Now, if you are using very high power receiver and you have some sort of a vacuum tube based power amplifier, which is old generation, of course, but they are definitely still used. You will be generating too much of heat inside the receiver. On the other hand, if you have a very low power receiver, which it could be very small. So it depends on receiver to receiver. But all these different types of noise sources must be taken into account. Noise factor. So noise factor is really a measure of noise added by the active devices inside the receiver. Or if, like somebody earlier pointed out very intelligently, that if you have a transceiver or transmitter and receiver co-located inside the box, yeah, of course you have to consider the noise added by all the active devices. Doesn't matter whether it is being generated by a transmitter equipment or receiver equipment, because they are in the same box. Any heat generated over there will be impacting the receiver side of the equipment. So it's the noise factor is, by definition, it's the ratio of the signal to noise at the input to the signal to noise at the output. Now this is a very standard definition, comes from basic physics and electronics, and you can always refer any textbook for that. It's a very standard diagram over here. And these are different variations of the same noise factor. This can be defined in 3 different ways. Basically, what we are trying to, F is noise factor. Noise factor. F means noise factor. Now again, to simplify this in terms of dB or decibels, we define a term called noise figure. This is 10 log of F. This makes it easy for our calculations. Now you see, it's very simple now. The noise figure is simply a difference of signal to noise ratio at the input and the signal to noise ratio at the output. We just subtract the SNR at the output from the one at the input, and we find out what is the noise figure of that particular device. This is often, if you look at any receiver specification, often they will mention this number actually. What is the noise figure of this receiver? That is what it means. So noise figure will be in terms of dB, and it's 10 log of noise factor. Well, this is again another very important observation. What if we have a cascade of amplifiers? Like you may have a low noise amplifier at the antenna, and you may have another front end amplifier in the receiver, and then you may have a IF amplifier in the middle stage, and then finally a power amplifier at the other end. So you have a cascade or a chain of amplifiers, and each of these amplifiers will have their own gains, their own temperatures, noise temperatures, and this Fry's formula here defines how do we calculate the noise factor of this chain, the whole chain actually. And you know, it looks like very complex here from the picture, but you don't need to go into all the full detail of this. The only observation here is that if you look at F1, F1 is a very bigger quantity compared to others. F2, F3, they have a lot of other quantities that get divided, very small contribution to the total F. So most of the contribution to the F of this, for this cascaded sources, is coming from F1 or the front end. So the front end amplifier is the most important contributor to the noise factor of the whole equipment. So that is why when you have a satellite communication equipment, you must have seen they always put a low noise amplifier or LNA or LNB on the dish itself, because that improves your signal to noise ratio by a big factor. You don't need a very high amplifier on the last stage, the power amplifier, but the LNA must be very good. That is because of this equation here. You see, the front end is the biggest contributor to the noise factor. So the amplifier at the front end must be the most powerful one. Okay. It's taking a little longer. I hope you can bear with me. We want to finish this. Okay. All right. So what do we have so far? See, we recall this receipt power level equation we had derived earlier, where we have the transmit parameters and the radio channel parameters and the gain of the receiver and the loss in the receiver. Now we have another equation for the noise power at the receiver. This is coming from the previous formula we had, where we just need a bandwidth, what bandwidth we are using, and what is the temperature, the equivalent temperature at the receiver side. And once we have this, we just calculate the result. What do we have so far? We arrive at a signal to noise ratio in dB, which is just a difference of in dB of PR and N. Receipt power at receive power level and the noise power at the receiver. And that's it. That completes our calculations. Now let's go through an actual example. We'll quickly go through this microwave link example. So here we assume a microwave link where the transmitter power is 5 watts, waveguide loss is 3 dB, and transmitter gain is 34 dBi. We arrive at a EIRP of 38 dBW. Next, what we do, we calculate the path loss. So here, first we calculate the free space loss. We input to the same equation we had before. We arrive at 122 dBW here. Then we add the atmospheric losses. We use for 1 gigahertz frequency, we use attenuation of 0.0025 dB per kilometers, and we have the atmospheric loss of 0.075 dBW. And just for simplicity, we assume additional losses of 0 dBW. Actually, 0 dBW is not really 0 watts; it is 1 watts actually. You know, see, remember we are using a decibel here. This decibel is with reference to 1 watt. So 0 dBW means 1 watt of loss. Okay. Next we obtain the receiver gain and receiver feeder loss. So receiver gain, this from the receiver specification, you can read this number. The gain is 34 dBi, feeder loss is 5 dB typically. Then we calculate the received power. Now we subtract the path loss and the gain of, add the gain of receiver and subtract the loss of on the receiver side and arrive at minus 55 dBW. This is the received power level at the receiving antenna. Now we estimate the natural noise temperature. So here we assume that the antenna, our antenna, now you see if you look at the tower, the antenna is like is vertical. The dish is vertical here, but it's looking at two side lobes. One side lobe is looking at the ground, and the another side lobe is looking at the sky. So we take the ground temperature is 290 and sky is 30 K. We take the average, which is 160 K. That is the average natural noise temperature here, 160 K. For the antenna temperature, we are assuming it's 290 K, unless otherwise specified in the antenna specifications. We take the feeder loss, which is 75 K, unless otherwise specified in the specifications. And for the receiver temperature, we usually have the noise figure mentioned, right? We assume a receiver noise figure of 6 dB, and from the equation here, the formula here, we calculate the receiver noise temperature to be 864 degree K. You see, this is the biggest contributor to the noise here. So we add up all these and we come at 1389 degree K. There is a comment here on a lighter note. Are these equations ever used in actual practical scenarios? Well, yes, but you know what happens? This is when we start from the ground up. But in practice, what happens? Like if you are in a cellular communication field working with a carrier, usually over years of experience, practical experience, they will have some thumb rules already built into their organization. Right? They over years they know, okay, if we have like if you are installing equipment in a metro area and this is the frequency, we already know, we have done this before. So they already know what should be the receiver signal levels, and it goes by that. But actually, at some point these equations have been used, or if you are installing equipment in a greenfield area where nothing is known before, it's a new type of situation, totally new type of situation, then the only resort is that you must go through all these calculations, right? So I hope that answers the question. So any organization, when it matures, it's in the wireless communication industry, yeah, they will have some, over years of experience, they will have some standard calculations already done actually. They know what type of signal level we need to do actually. But like if you are coming into new technology, like suppose LTE is being installed, 4G wireless broadband. This is entirely a new field, so somebody has to go through all these calculations again. It's not, LTE is not the same as GSM. It's a different frequency, different modulation techniques, and different application areas. Maybe you are putting more LTE towers in the downtown areas and less in the rural areas. So all these calculations do come into picture actually. Any RF optimization engineer who is hired by any company, he's supposed to know all this actually, how to do this. If you don't know how to do link budget analysis, you won't be hired probably. Okay, let's move on. Now let's calculate noise power at the receiver. We had the total noise temperature at the receiver calculated to be 1389 degrees K, and we are assuming a bandwidth of 10 megahertz here. So we come at minus 127.17 dBW. Now it's very simple to calculate our signal to noise ratio. We have a signal to noise ratio of 72.17 dBW here. Well, now this is a we put all this thing together and see in the form of a bar chart how our calculations look like. See, in number 1 here, we had a transmitter power of 7 dB. We had a loss of 3 dB and we reduced the power to 4 dB. Then EIRP, we have a gain of 34 dB. The effective power is 38 dB now. So we have a higher bar here. Then we have a path loss. You know, this is the biggest I will say nuisance, which decays the power by 122 dB. It goes down to minus 84 dB. So where we were in number 1 and where we are here in number 4. And then we have other things going on here. We have receiver gain. So receiver gain pushes up the level a little from 84 to 50, from minus 84 to minus 50. And finally, we have some receiver losses too, and ultimately net receiver power level is minus 55. And this is the noise floor. Now, what is noise floor? This comes from the calculation for the noise power. You know why this is important, noise floor? It's very important because we know that our signal level must be higher than minus 127. Like if our signal is not as high or not higher than noise floor, what will happen? Our noise can drown out the signal. The signal will be lost in noise itself. So this margin is very important between the receipt power level and the noise floor. Now next we come to this term we use, fade margin or link margin. So as we see from our calculations, the difference between the receipt power level of minus 55 and the noise floor of minus 127, we have a difference of 72 dB. So we have very good margin. That means our signal at the receiver is strong enough actually. It can overcome noise at the receiver and still a very strong signal, right? But we have to see that how much of fade margin we want to accommodate here. Remember previously we have small scale variation, fading effects. So like in a real handset cell tower scenario, when you move from location to location, your signal will fade. And how do we overcome those effects? We need to have a margin here. That is called fade margin. Okay. So this is a very general Rayleigh distribution which can be used to estimate the required fade margin. Like fading effects are changing with time, right? They are changing with location. They could change with time also. Even if you are at the same location, the atmosphere will change or something else will change and signal will fade. Signal level does not remain the same throughout the life of the equipment. It will change from time to time based on environmental effects. If you are moving or mobile based on your location inside the building or outside the building. Now, based on this is a thumb rule for actually microwave link towers. It may not apply to all other scenarios, but for cell towers, for microwave link towers, if you want your time availability to be like 5 nines, 99.99%, you want your signal to be available almost all the time, then required fade margin is very high. It's 48 dB. This is the ideal case. Like I want my signal to be available all the time so that I do not suffer any bandwidth degradation or anything else. So let's use this table to have an allowance for fade margin in our calculations. Now, if I have a fade margin of 48 dB, I'm still above the noise floor. You see here, my receipt power level was minus 55, but I am assuming that my signal might fade by 48 dB. It's a very, very stringent requirement, but it's applicable here. So I can still accommodate fading effects here in my particular calculation because to begin with, I had a very good total margin of signal to noise ratio. So I can accommodate a fade margin of 48 dB here, and that will define my receiver sensitivity. Well, this is the receiver sensitivity I'm arriving at by my own calculations. That means I can have any receiver which is as sensitive as minus 103 dB. Of course, the more sensitivity, the better it is. But my tolerance for sensitivity is for any receiver will be minus 103 dB. The receiver that I use for my application must be able to detect signals up to minus 103 dB. Okay. So now let's go a little to a different type of application, a digital wireless communication link. Somebody had asked this question that whether when the signal level drops, does it affect the bandwidth? Yeah, of course it affects. If you are falling below your sensitivity level, your bandwidth degrades. And there is a term for that called BER, bit error rate. We always talk about bit error rate, BER, of a digital communication link. And EBNO, this is a measure of signal to noise ratio per bit. See, now we are coming into digital domain. We are not concerned about analog signals, but the digital ones. We want to know what is my signal to noise ratio per bit of transmission, where EB is defined as energy per bit, and N0 is the noise power spectral density. These are technical definitions given here below, and the usable formulas which we can use in terms of dB. Well, okay. So for all practical purposes, we use this formula. And for any digital communication link, EBNO is a very important parameter that is defined. You see here we are assuming a very simplified scenario of a microwave link, and that serves well for our simple scenario. But of course, this EBNO will change according to modulation techniques also. Like if you're using OFDM or using QAM or using QPSK, or what modulation techniques you are using. Okay, somebody asks, why is log R? Now this is a result of converting the basic equation from physics into decibel form. This we are writing in decibel form actually, right? Where everything is in decibels. That is how we have a log of R. We are taking log of both sides of the equation, or the basic equation, and then we get into this. So for that part I cannot cover in this webinar. You have to go to the basic equation or the physics here. I just directly mentioned the dB form of the equation and just using that here, because this is the one that I'm going to use in my calculations. Because I'm taking a log on both sides, that is why. So now here, this is a practical example. Let's say that in our previous example of link budget analysis, we had a receipt power level accounting for fade margin, it's minus 103 dB. Now let's say we have a data rate of 1 megabit per second and equivalent noise temperature of 1389 degree K. So EBNO comes to be 34.16 dB here, right? Very straightforward calculation. You can use a calculator to the logs also here, but very straightforward. Now there is some relationship between the bit error rate and EBNO. Now there are curves published online by ITU, BER versus EBNO. So those curves can be used to analyze this behavior. For an example, if we take a bit error rate of 10 exponent minus 8 and we assume our modulation is QPSK, quadrature phase shift keying, then the required EBNO is determined to be 12 dB. This comes from the charts published by ITU. So what that means, that at 1 megabit per second, our available signal to noise ratio per bit, or EBNO, is 34 dB. Now let's recalculate EBNO for 100 megabits per second. Let's increase the data rate, right? We are not changing anything in our wireless link. It's the same tower, same distance, same receiver, same noise power, everything. But we want to see that what happens to our EBNO at 100 megabits per second. Now you see, after the calculation, it gets reduced to 14.16 dB. Whereas at 1 megabit per second, we had 34 dB. At 100 megabit per second, our energy is much less, 14.16 dB. But still, if you look at the upper requirement, our required EBNO is only 12 dB. Still, we are within the range. Well, somebody commented, isn't that contrary? Well, you know, here we are talking about data rate. We are not talking about frequency here. The available bandwidth and whatever data rate we can transmit. So what we are trying to emphasize here is that there is a limit to how much of data you can transmit at a given EBNO or at a given signal to noise ratio per bit. So we have a different focus here. We're just trying to determine what is the limit to our data transfer rate for a given EBNO, right? So this formula will help you determine that. Now next, let's say we talk about LTE, which uses OFDM, or wireless LAN IEEE 802.11 AC version, which has OFDM. Now OFDM, there may be a different requirement, right? Here we see, that's why I mentioned this from the curves. If the modulation is QPSK and bit error rate, that means you have to tolerate this much of bit error rate too. Then the required EBNO is 12 dB, right? Now you could reduce your bit error rate, then maybe required maybe much higher actually, right? So these are all within these boundaries you have to design your link, right? So you have to know what is your digital modulation technique and what is your acceptable bit error rate, and that will tell you what is your required EBNO, and you have to design your link around that requirement. So these factors will come in when you are actually designing your link for a certain modulation technique and for a certain acceptable bit error rate for a link. Okay, let's move forward. Now, for satellite communication link, there is another thing that comes in, figure of merit. Figure of merit is nothing but the ratio of antenna gain to noise temperature of the antenna. So again, the Intelsat, let's say for an example, the Intelsat earth station requirement is like for frequencies of 3.7 to 4.2 gigahertz, your figure of merit must be more than this expression. What is that? 40.7 plus 20 log f by 4 dB per Kelvin, where f is in gigahertz. Now this is a requirement arrived at through some modeling, right? These are published online. So you have to use this requirement when you're designing a link for satellite. As an example, if you have, let's look at this example. What does it tell us? So we have a frequency range of 3.7 to 4.2 gigahertz, and our requirement is that. Let's assume that our receiver gain is 60 dB and frequency is 4 gigahertz. We arrive at a temperature of 85.13 degree K. Now what does it tell you? For satellite communication links, our temperature has to be much lower actually. You know, in our earlier calculation for earth-based microwave towers, we were talking about a total receiver temperature. It was coming out to be like 1389 degree K, and that was for the total receiver and the antenna. But just for the receiver here, it has to be 85.13 degree K. Otherwise, your signal will be lost in deep space. You cannot simply make out signal from noise. For this reason, most of the commercial satellite links which are used for broadcast TV, they have low noise amplifiers and LNBs or LNBs installed at the receiving antenna, right? That helps to overcome the noise level. And the primary reason for that is because the signal level is so weak because of the distance that it's almost indistinguishable from noise, and you must have a front end low noise amplifier. Now for deep space communications, they may have to be supercooled antennas, receiver antennas, the kind that NASA or any other space organization will use. And in any country, they have to use supercooled antennas. The objective is to bring down the temperature of the antenna so that there's the noise level. Right? Because see, signal level is what it is. What we are receiving, that is the signal level. So you could do everything. You could have a higher transmitter gain and all that stuff, but there are restrictions or limitations. So the other approach for deep space links are deep space communication link is that we reduce the noise level of the receiving antenna itself by supercooling the antenna. Okay, I think we are at the end of the webinar now. So this is a reference of certain research papers and books that can be used to dig deeper into any of these topics. So this finishes our part 1 of 2 of link engineering. The second part will be will happen 2 weeks from now. I think it's June 15th, right? Some of you might have registered for that. So we'll cover more interesting topics in that area and go into statistical fading models and how to apply those models in different situations like indoor propagation and outdoor propagation, cell sites, 2G, 3G, and all that stuff, right? So, but again, it will be link budget analysis applied to all those different situations. So there is a question here before we end. How do you maintain an antenna at that temperature? Well, that is what I said. You have to have physical methods, different methods of cooling the antenna. You could cool with water, you could cool with liquid hydrogen, liquid nitrogen, or what have it. So you have to employ different techniques to cool the antenna. That is why I said supercooled antennas. It's a very general, broad term, but ultimately we have to cool down the antenna to bring down its noise temperature. Okay. Well, yeah, of course, I can send the copies of these slides to email to you if any one of you needs it. I'll send it out to you. Please send me a request in email, and I'll send it to you. And now, coming to the certificate of completion and how do you earn the professional development hour. So after the webinar ends, you will be redirected to webinar forum page at this link. You can note down this link, or you will be redirected to this link, where you are supposed to complete a feedback form, and there is a problem statement from this webinar. Like there is a certain scenario and you have to answer. You have to provide an answer or a solution to that problem actually. Very simple one, just based on this webinar. Don't be scared. I'm not doing a test or exam. It's just to complete the requirements of the webinar. I need to have something from you so that I can give you a certificate. And after that, I will email you the certificate of completion within 2 business days. You can always reach me. My email ID is there on the slide. I have a LinkedIn profile. You can Twitter me, or you can visit our website to learn more about our other services. Before that, are there any questions I can answer right now? Okay, so then, well, there's a question so I keep this time so that everyone, I don't change time very often. I just keep this time always, so that people know that this is the time that they will have webinar. But then it may not be every Saturday. Like you have to find out when it is happening. Like the next one will be happening on June 15th. Okay, any other question? Okay, so I got requests for the slides. I do send email to you for the slides. And if you need a certificate of completion, please complete the requirements and you will get that too. Okay, then so we'll end this webinar. Thank you very much. Even after this, you have any questions, you are most welcome to send me email